Assalamu alaikum everyone. This is lecture 4 on nonlinear control system, EEE 6701. We are discussing chapter 2, phase plane analysis. In the last class, we have seen few examples. Basically, those are actually taken from different sources of internet to make things easier for you. So today we'll actually continue with another example, this time with a nonlinear, one of the nonlinear system. And then based after that, we'll actually go back to the chapter 2 again. Okay, so going to cover the topics in sequence. Now here, just consider a nonlinear system that is a pendulum, a freewheeling pendulum. So we'll try to figure out the corresponding transfer function of the pendulum, and then we'll find out its corresponding state space representation, then the steps that we have followed, actually the uh, equilibrium point, then eigenvalue, eigenvector, then finally going for the phase portrait. But there will be one additional point here, and that is because of the fact that the system is nonlinear. So at some point, we actually have to linearize the system. Then we can actually go for the system's state space representation of the system. So now let's start. Say we have a system of the pendulum with a pivot. The pivot basically pendulum is hanged, and this is the reference axis. So at any point in time, this is the location of your pendulum. The pendulum has a mass m, and it has, say, the length here is L, and we have a gravitational force downwards. Okay. So pendulum's direction of the rotation will be actually moving in this way. And let's say the angle with the reference is theta. So you can also write theta t, time variable. Okay, so now we have to, since it is a rotational system, we have to write a rotational equation. So motion of the pendulum we have to figure out. Okay, so motion of pendulum. Okay, we assume theta t is the position of the pendulum. Position of the pendulum. So the system's dynamics will be represented by the second law of motion. So second law of, to be specific, rotational motion. Okay, so as we say, this is the length L from the pivot to the object M with mass M. So now, what is the second law of rotational motion is summation of the torque should be equal to inertia, moment of inertia times the angular acceleration. Okay, so what is alpha? Alpha is theta double dot, double differentiation of the angular position. Then what is I? Inertia, m into length square, so ml square. And the torque that we have here, actually only one torque is available, and that is the gravitational torque. Okay, so gravitational torque, and which is by general formula, that is minus r f sine beta. What is beta? Beta is basically if you extend the angle here, then whatever the angle with your gravitational force. This is your gravitational force. Okay, or gravitational. So as we know, beta is nothing but actually sine theta. Beta is same as theta. So r, the length here is minus L, and gravitational force is mg, and then sine theta. Okay, so if we put everything into the equation, then what we are going to get is, let's have the pictures at the side. So something like this. M torque is basically minus L mg sine theta, and moment of inertia, you can take it to the other side. So what you're going to get, m L squared theta double dot. Okay, so this is the equation. So some parameter can be cancelled like m and L. So basically what we are going to get is theta double dot. Secondary derivative of the theta is basically minus g by L sine theta. So the first thing that we should do is to find out the nonlinear parameter of the differential equation here, sine theta. And now let us try to find out the equivalent. First of all, actually, we have to find out the state equation. So state equation is state one in this case. State one is state equations. Okay, so basically the evaluation of state equation. Okay, so what we can assume is theta dot can be phi, okay, and theta phi dot, which is theta double dot basically. So phi dot will be the rest of the parameters. So minus g by L sine theta. Okay, so this is our system. So now if you want to represent in a matrix form, the difficulty here is basically this nonlinear one. So we'll be applying the linearization, and before that, in the step 2, we actually have to figure out the equilibrium points. Okay, so let's try to figure out the equilibrium points first, then we'll go for the matrix. And okay, so that was step 1. Now step 2 is basically linear, finding the equivalent points. So, or sometimes it is called critical points, critical or equilibrium points, okay. So now how to do that? Basically theta dot should be equal to 0, as well as phi dot should be equal to 0. So now this will give us this actually implies that phi has to be 0. Okay, so first equation. And the second one is actually sine theta should also be 0. Now the point here is sine theta is 0. This gives us 3 cases. So first case is whenever phi equal to 0, there is a critical point phi equal to 0, and your theta equal to 0 as well. This is one critical point. Then another critical point is theta equal to 0. Sorry, phi equal to 0 always, and theta equal to plus phi. And third one, phi equal to 0 and theta equal to minus phi. Now there is one thing you always have to remember, that what are their physical significance. So that thing you always have to keep in mind before actually apply going for this uh, stability analysis or state space analysis of the system. So what does it actually mean is uh, the first equilibrium point is 0, theta equal to 0. That gives actually physical interpretation. If this is your pivot, this is your mass, this is your angle 0 degree, this is your one critical point 0, 0. And the other one is vertically upwards. Okay, so vertically upwards. Sorry about this line. It's better to use the ruler. Okay, so vertically upwards lines. So actually the downward is also not that perfectly drawn. So, okay, just assume that this is your vertically upward line and this is your vertically downwards line. Okay, so now since this okay, so this is 2 point. This is your phi equal to 0 as well as theta equal to 0. And this is say minus, this is your plus pi angle plus pi, and this is your minus pi. Essentially, they actually represent the same location. But this is not only the two solution, because you can have a family of solution like pi, 3 pi, okay, so 5 pi. So it will be like this. So basically n pi can be one of the cases. And similarly minus 3 pi, minus 5 pi. So, but essentially they represent the same solution. So there we have taken the first one. And now let us try to figure out what are the corresponding phase plane for these particular cases will be. Now let's start with the first one, theta equal to 0 and phi equal to 0. Okay. So before going to that, as we said, we have this is a nonlinear system. So yeah, always have to linearize our system. So that will be, I think, step 3. Step 3. So this is linearize around critical point. So we are discussing with the first one. So 0, 0 critical point. Okay, 0, 0 point. So we know that we have to assume phi equal to phi critical plus small perturbation. So del phi. Similarly, theta will also have to have a small perturbation about the critical point. So theta c, and then you have del theta. So basically, these critical conditions are 0, both of them. So we can say that approximately phi equal to del phi, phi equal to del phi, and theta equal to del theta. Okay, so now let us write the differential equation. So if you differentiate these two, then what you can find is phi dot equal to actually del phi dot, and theta dot equal to del theta dot. Okay, so this is the case. Now also we have to find out the sine theta, the linearized version of sine theta. So sine theta, if you go for the Taylor series expansion, then we'll find that sine theta can approximately, obviously first of all theta has to be replaced by del theta. Then according to your Taylor series expansion and just considering the linear component, we are going to get del theta, sine theta equal to theta. So sine del theta will be del theta approximately. Okay, so you can give the condition that del theta is very, very negligible. So very small perturbation. Now, here you can also verify that thing using your Taylor series expansion of sine x will give you basically approximately x minus x cubed by 3 factorial 3 plus goes on. So basically, we are just taking only the first component, which is linear, and that is why sine theta, sine del theta equal to del theta. Okay, so now we have to write the state equation. So our state equation will be the first parameter is del theta dot equal to actually del phi. Okay, from where it is coming, so the equation that you have derived here. So for del, sorry, theta dot equal to uh, phi. So del theta dot will be equal to del phi. Similarly here, phi dot equal to this parameter. So sine theta will be simply replaced by del theta. Okay, so we'll have the equation like this. So del phi dot equal to minus g by L del theta. So now from this one we can represent this thing to a vector form. So say this is our vectors. Del theta dot del phi dot equal to, we have 0, 1, and then minus g by L and 0. Okay, so this is your system matrix with your del theta and del phi. Okay, so this is your matrix A. Now, next step, I think it is step 4. Step 4, few additional steps actually you had to add for the nonlinear system. So step 4 will be finding the eigenvalues first, then vector basically. So eigenvalues. So how to do that? Uh, determinant of lambda I minus A. Okay, so this has to be equal to 0. So basically lambda 0, 0, lambda minus 0, 1 minus g by L 0. So you have to find out the determinant of this and you have to set it to 0. So what you are going to get is lambda minus 1, then you have g by L, then we have lambda. So basically lambda square minus it will be plus lambda square plus g by L equal to 0. So next is lambda value is basically minus g by L, root over minus g by L. So basically plus minus j root over g by L. So what does it mean? It is a pure, it is a imaginary number. So imaginary number, and we know that imaginary number means that there will be some oscillation available. So there will be no exponential growth or exponential decay. So actually, if there is no energy dissipation, the interpretation of this one means that around the equilibrium point origin, so you will always have a circular motion. Okay, something like this. So this is what is going to be like. I think I also have shown you how to find out the direction. So you have to just take arbitrarily any point, then multiply the system matrix, and then you can figure out what will be the in which direction it is going. So this is in phase plane what it means, circular motion, and physically what it means. Your mass will be actually rotating around the origin. So if you are giving a theta value for different theta value, you have a different oscillation going on. Okay, so this is what is meant by the circle. So ideally, if there is no energy dissipation, so it means that whatever the theta you are giving, it will always oscillate around that theta value if there is no friction or anything else. Okay, so this is the representation for yours, one of the critical point. But we have two other critical point. So let's focus on the next critical point. That is next critical point is say theta c equal to theta c equal to plus pi and phi c equal to 0. So let us consider this one. So now again, what will be our equation? Then basically phi, our theta will be theta c plus small perturbation, that is theta del theta, and phi will be uh, phi c with small perturbation. Okay, so now this previously both of them was 0, but this time actually theta is having some value pi. So what will be the scenario here? Approximately is pi plus del theta, and this will be del phi again. Okay, so from this one, now if you differentiate theta, or sorry, it should be theta first. Okay, so theta dot will be actually the pi is constant, so del theta dot. Okay, and phi dot will be del phi dot. Okay, so now also the nonlinear thing we actually have to consider about it. So del theta is now del sorry, sin theta is now sin pi plus del theta. Okay, so now actually we are in this coordinate somewhere here. So here sign is negative, so it will be just minus sine del theta. And we know that with the linear model from the Taylor series expansion is sine theta equal to theta. So basically minus del theta will be the case. Now based on these parameters, if we try to find out the equation, then what we are going to get is, okay, so del theta dot will be del phi based on the previous equation basically, and del phi dot will be this time it is because of the minus, minus and minus will be getting plus, so basically plus g by l del theta. So now let us try to write it in the matrix form. So we have del theta dot del phi dot will be equal to, what we have is 0 1 g by l, and this is 0. We have del theta del phi. Okay, now here you can see there is only a slight change. That is, previously here you have negative sign, now it is plus. And let's see how significant is this change in terms of the phase plane analysis. Okay. Now, as we know, that next step is to find out the eigenvalue. So from the eigenvalue, if it is imaginary, we don't have to, or complex, we don't actually have to go for that eigenvector, because of the fact that we know that there will be spiral, exponentially increasing or decreasing, or constant magnitude. So, but if it is having some real values, then actually we have to go for the eigenvectors. So let us try to figure out what is eigenvalue first. So del lambda I minus a equal to 0. So lambda 0, 0, lambda minus 0, 1 g by L 0 equal to 0. So basically lambda minus 1 minus g by L lambda. And now what we have is lambda square minus g by L equal to 0. So lambda equal to plus minus root over g by L. So this is a real number, and as you can see, one of the root is plus, so which represents growth, exponential growth, and the other one is minus, which represents decay, exponential decay. Okay, so we know that this kind of scenario is called saddle node or saddle point. In one direction it is stable, in another direction it is unstable. So let us try to figure out the phase portrait for this one. And for that, because these are real quantities, so actually we have to go for the eigenvectors. Eigenvectors. So basically lambda, so ax should be equal to lambda x. So there is two values. So say the lambda equal to plus g by L root over g plus g by L. Then what will be the case? Okay, so A is basically 0, 1, g by L 0, and say your x is del theta and del phi. Okay, so this will give us root over g by L, which is lambda, and then your d del theta, del theta and del phi. So now, if you, we know that both the equation will give same, so we can just write one, but still it's up to you. So del phi, sometimes dels get confused about this. Del phi should be equal to root over g by L del theta. So this is the equation, and the other one will actually g by L del theta should be equal to root over g by L del phi. So basically you can just cancel out this one, and eventually it will remain same whatever the scenario. It always gives the same equation. Now here basically what we get is this equation del phi equal to root over g by L del theta. Now root over g by L del theta sometimes may get us confused. So we're just assuming that the gravitational force is 9.8 meter per centimeter square. So basically we can actually assume that the length is also 9.8. So just make it 1 so that our calculation becomes easier. So basically we can assume that this is just an assumption that del phi is approximately del theta. So basically our eigenvector can be assumed as all equal magnitude. So say 1, 1. Okay, so this is one of the eigenvector. So 2, 2, 3, 3, 4, 4. So equal magnitude, whatever it is, can be an eigenvector. Okay, so similarly, we can actually go for the next one. So next one actually, let's me side by side will be easier. Okay, so what will be the difference? Difference will be, so lambda, for lambda equal to minus root over g by L. So the difference will be only into the equation here. So this portion will be minus. So what we are going to get here finally, the equation is del phi should be equal to minus root over G by L del theta. Okay, so this is the only change. Again, for simplicity, we are assuming G equal to L. So basically, del phi will be minus del theta. Okay, so one of the eigenvalue is 1 minus 1. Eigenvector. Okay, so this is just I have taken a bit of simplification so that it doesn't take too much time to explain what is happening here. Now, we have the eigenvectors around the point 0, basically pi 0. So let's try to draw this. Okay, so let's take an axis. I think more space will be better. Okay, so this is the axis now. Now let's find out the points. So one point we already figured out is actually this one. Okay, and another one, say pi. Uh, okay, so pi 0. So that is approximately 3.14, something like this here. 3.14 somewhere here. So we just calculated this one. This one is having a saddle point because one of them is having exponential growth and one of them is exponential decay. So 1, 1. So basically it means 45 degree and 1 minus 1 is minus 45 degree. So we'll have saddle point something like this. Okay, and similarly, actually you can plot both together because the other point essentially the same point, vertical point. So if you calculate, you are going to see the same eigenvalues and eigenvectors. So we'll have something like this. Okay, so draw the other one. The one that we drawn is minus 45 degrees. Now also draw plus 45 degree. Draw in both cases. Okay, now we know that 1 it is for 1 is giving us we are obtaining 1 from plus eigenvalue. So 1 is obtained for plus. That means this will give you exponential growth. Okay, so it means this one will give you an exponential growth in both direction. And 1 minus 1 is actually drawn for negative eigenvalue. That means it will be exponential decay. So this should be the direction for this one. So that is why this point is called saddle point. Now, similar thing because they are identical. So these two will be exponentially decaying and these two will be exponentially increasing. Now, to find out the complete picture, we can draw a circle here around this origin. Okay, so circle. So oscillation, the direction can be clockwise if you just multiply the eigenvalues, system matrix with any arbitrary point. Now, what about the rest of the case? So rest of the case, if you extend, it will be something like this. And you can also join these two. You'll have something like this. So this will be your direction. So in the inside, you'll have an oval shape, something like this as well, maybe. available. So this is your face portrait inside, and outside you can just erase those to make it look good. Okay, so in the outside, what will happen? Outside, you'll have a saddle point, something like this. Okay, so you have a direction like this. You'll have a direction like this in the downwards as well. This will be your system's face portrait. Okay. As well as here, you'll have a direction, something like this. Okay, so these two are actually unstable points, as you can figure out already, because once you're in a vertically up, a small perturbation in any direction actually let your pendulum fall down. So these are actually unstable modes or critical points, and only stable critical point is this one, that is straight downwards stable. Is it okay? So this is how you have to, for a nonlinear system, this is how we have to figure out the phase portrait of the system. Nowadays, actually, there is a computer available. So if you just give the system equations, automatically this thing has been calculated. Okay, so nothing to worry about. So these are the few examples I actually obtained from several online tutorials or resources, and I try to make it clear to you so that with the example things actually become easier. So now let us go back to the contents of the chapter 2 of the Applied Nonlinear Control book. And here, I think the next topic is how to construct the phase portrait. Even though I actually have studied few methods, but it is always better to comply with the book. So constructing phase portrait. Okay, so there is a few methods. One is called, the first one is analytical. Then we have a method of isocleans. Then we have delta method. Then we have Leonard's method. And finally, Dell's method. So in this book, actually, they have covered the first two because they claim that these are the easiest one, even though actually all the methods are nonlinear. So sometimes they're actually complicated to figure out. So let's start with the first one, analytical method. Analytical method we already have seen in example 2.1. We already have seen analytical method. And bottom idea is to find out a relation between the two phase parameters, like a function something like this, x1 in terms of x1, x2, or maybe some constant. Okay, so C can be initial condition, conditions, or sometimes external input. Okay, so this is C, and you don't get confused. X1 can be actually your X, and X2 can be your X dot as well, or it can be X, and this can be Y as well. So different notation is actually possible. Bottom line is time variable has to be eliminated from the equation. The first method, there is also two methods inside this analytical one. The first method is the one that is we have seen in your example 2.1. The first method is basically what we have done is x1t was we have say we have g1t, and x2t is g2t. So both of them are actually function of time. So what you have to do, we have to eliminate the time t from these two equation and leading to a functional relationship that we have talked previous one. So we have to find out after eliminating the time variable t, we have to find out the relation between x1, x2, and some external conditions maybe. So this is what you have to do, and this is what you have done in example 2.1. Okay, so we have find out some solution sine t cos t differentiation of which then ultimately we just have a relation between x square x1 square plus x2 square equal to x0 square and initial condition, something like that. So next method is pretty straightforward. The next method, second method is straightforward. What you have to do is once you know the two equation, so you just divide one by another. So basically what we know that x1 dot was a function of x1 and x2, and x2 dot equal to actually function of x1 and x2 again. So now these two are basically dx1 by dt, and this is nothing but dx2 by dt. So if you just divide 2 by 1 directly, then what we are going to get is dx2 by dt, sorry, dx2 by dx1, time variable is eliminated, dx1 equal to f2 x1 x2 by f1 x1 x2. Okay, so pretty straightforward. So let us see one example. The same example is example of same problem of example 2.1, but in a method, second method. So basically what we have, example 2.4. So x double dot plus x equal to 0. So as you can see, there is damper missing. So basically this is the example of, I think, mass spring. Okay. So first thing that you have to do is this is time variable has to be vanished. So the time variable is available here only. So this is nothing but you can write x double dot equal to dx dot by dt. Okay, so we can further write in this way, dx dot, we introduce dx here as well as dx here. Then we have dt equal, okay, so now actually we can write this parameter as dx dot by dx, and this is nothing but x dot as well. So if you put this quantity into this equation, then what we get is dx dot by dx x dot plus x equal to 0. Now if we multiply with dx, we have x dot dx dot plus x dx dot equal to 0. Now if you integrate in the both side, then what you are going to get is x dot square by 2 plus xs square by 2 is equal to some constant c. So x dot square plus xs square equal to twice c. So twice c can be considered as a x0 square, whatever the value, just we make it as a square term. So now this represents the same solution as before. So this is a circle equation. So now your face portrait is same as before. So always you will have something like this. Okay, so let us take another example. This is a simplified satellite example, example 2.5. Example 2.5. So in this particular case, we have a feedback system, unity feedback system with a nonlinear control here. Okay, so now you have 1 by p. So just for your ease, p here represents the same as your Laplace transformation parameter. There is 1 by p is just nothing but an integration. Okay, so this is oversimplified representation of your satellite. So simple satellite model. Okay, so this is your theta output, and here it is becoming theta dot, and this is your input u, and this input has only it has two output, basically plus u, capital U, and minus capital U. Okay, so this is maybe the jet. So satellite is been following a simpler model, something like this. Okay, so well, this is, let me try it again. Okay, so this is your reference axis, and whenever your satellite is moving with an angle, say theta, something like this, with an angle theta. Okay, this is an antenna. Then there is some thruster or jet effect. So using which actually it will try to oppose the direction of the rotation. Okay, so it will try to get back to your initial position again. So this is the input that we are trying to apply. Now, this model, so even though this is a mechanical model, we don't know much about it, but it doesn't make any difference once we have the block diagram of the system. So we'll actually focus on that one, apart from getting too much involved into whatever they're saying. Okay, so what we are doing here is basically we're just considering the system here. So from this block diagram, as you can see, this is theta dot here. So it should be theta double dot here. So we can say that theta double dot should be equal to u. So this is our very simple system. So we don't have to be getting too much confused about it. Now, what is u? Use the control law or control input. Control law is something call it, and this is what has been given as in the figure says, minus u if theta is greater than 0, and plus u if theta is lesser than 0. So basically, if theta is clockwise, we are giving anti-clockwise force, and if theta is anti-clockwise, then we are giving it clockwise force. So it is not that complicated. Okay. Now we have to find out the mm, phase portrait of this particular system. So I'm going to do that using the direct method. So our equation is very simple as it is theta double dot equal to u. So theta double dot can be written as d theta, same as before, d theta dot by dt equal to u. And then we can introduce d theta by d theta dot by d theta, and this is how the same approach that we have done. Okay, so say that we are using the first case, that is here u equal to plus u. Okay, so we can just replace this by plus u. Because we have two different conditions, so we have to actually find out the phase portrait for both of them, then we have to combine those together. So now here, as you can see, as before, d theta dot by d theta into theta dot equal to u. So theta dot d theta dot equal to u d theta. Now, if you integrate on the both side, what you're going to get is theta dot square by 2 equal to u theta plus c. Okay, so you just multiply with c 2, then theta dot square equal to twice u theta plus twice c can be written as c1, just the coefficient, so it doesn't make much difference. Now this is actually a parabolic equation, so your system will have something like this. Okay, so some parabolic with the different values of c, you're going to have different uh, parabolas. Okay, and the direction same with the eigenvalue, you can easily figure out what will be the direction. Okay, so this is if u equal to plus u, capital U. Now, if u equal to minus capital U, so if u equal to minus capital U, in that case, some more or less similar equation, except that we'll have a negative sign here. Okay, so let's write that thing. So theta, say theta dot square, theta dot square equal to minus twice u theta plus c2 maybe. Okay, so now it will have the same thing except that it will be in the reverse direction. Okay, something like this. Okay, so this is the direction of the rotation trajectory. Okay, so and this is your theta, and this is your theta dot. So theta, and this is your theta dot. Now, if you combine those two, then what we are going to get is a combined phase portrait, and this will be something like this. Some ovals will be coming out. Okay, so there is a direction something like this. Some ovals will be coming. So ovals and circles, they actually represent same thing. They actually give a oscillating nature. So what does it mean? The system will be behaving, or will be starting oscillating once your theta value is being changed from 0. So that is your reference value for theta, so theta equal to 0. So once there will be a slight movement of your antenna, okay, so it will always start vibrating around this point. Okay, so this is your phase portrait of a simple satellite system, and we can say that the system is actually marginally stable. Why marginally stable? Because you have oscillations neither increasing or decreasing. So these are marginally stable system. Okay, and also one thing, whether you have noticed or not, there is a change of direction in the vertical axis. This is also coming because of the fact that whatever the input we are giving, that is also we are changing that around the vertical direction, plus u or minus u. Okay, so that is why, and this is also linked with the direction of the phase being changing in this particular case, one going clockwise and the other will going anti-clockwise direction. Okay, so this is more or less how using the analytical method to figure out the phase portrait of a system. So next method is methods of isocline. So I think it's the class is almost 1 hour. So, and also if we start the method of isocline, it will take 10 or 20 minutes more. So I believe we can stop here. In the next video that we are going to upload, we'll be discussing the method of isocline, and then we'll proceed in accordance with the articles given in that particular book. So the next class, inshallah, we are going to discuss method of isocline. Okay, so in the meanwhile, one thing that we already said that there is no straightforward way of doing things. Rather, sometimes it is based on intuition, and it's always better to know the different methods because for some method may be easier to implement, and for some other system, maybe we will have a different choice, suitable choice. So that is why the more method you know, in case of the nonlinear control system design, it is actually better for us to go for the systems because sometimes you will have different kind of nonlinearity like chaos or a limit cycle or bifurcation. So there is no straightforward or rigid rule that for this particular nonlinearity you have to apply this method. Rather, we actually have to switch between the methods based on your how easy it is to apply on a particular control system. So let's discuss those things in the next class, inshallah. See you in the next class. Assalamu alaikum.